And I'm starting recording this too. Out. And I'm starting recording this too. Okay, so we are 1:06. This is day 3 of our class. We have 35 participants so far. That's good. And we are day 3 wise. We were supposed to read through these number systems. Like this is the topic for lecture 3. I didn't see any question over the discussion board. If you have any question, you can ask now on these or any other topic.
Yeah, I have a question.
Yes.
Can we do an example of going from 2's complement binary to signed decimal? That's a little confusing for me.
Okay. 2's complement. Okay. Just let me see. So you're saying that you start from the binary pattern and then you want to go to the decimal value.
Yes.
Okay. Let's first review that corresponding lecture notes and slides, what it says, and then we'll go from there. So lecture 3. Okay, let me share. Right. Okay. Do you guys see my slides there?
Yes.
Okay, good. So the 2's complement was discussed here. So this was giving an example of converting from decimal to the binary pattern. Now, what Matthew says, asked about how can we, from a given bit pattern, how can we go back to the decimal value, right? Why don't we do it in a reverse fashion, right? So we know this pattern, and this would be our decimal value, right? So let's try to do it. Let me share. Let me just bring it my Jammer, not Jamboard, which is, where is my Jamboard? Or maybe I can just share the screen. Okay, so in that slide number 22, we have this binary pattern, right? It is 1 1 0 1 1 1 0 1 0, 1, 1, 0. So, and also the important part to know here for any 2's complement form is that how many bits we are talking about in this representation. So it is 8-bit 2's complement. So it immediately gives us this information that the lowest integer value is minus 2 to the power 7, right? So basically, which is like 32 is 2 to the power 5 is 32, 2 to the power 6 is 64, 128. So minus 128 in base 10, right? So that is, and that is the value represented by 1 0 0 0 0 0 0 0. So 8-bit 2's complement, this bit pattern is minus 128. That represents minus 128. So here, what we shall do now, we look at these. We first separate them out into two parts. One is the leading most, and then the rest 7-bit we convert into a decimal, an unsigned decimal. Okay, so that will be for us is this is 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, right? So 0, 1, 1, 0, 1, 0, 1. Right, that means we need to add up 2 to the power 6, which is 64, this one, plus this one coming up as 2 to the power 4, which is 16, plus this one is 4, plus this one is 2, which is, now it will give us 20, 22, 82, 86, right? Now, so this bit pattern, this part, right? This part represent 86. The other part, like 1 rest of 0, 0, 0, like this one is minus 128. So that means 1, 1, 0, 1, 0, 1, 1, 0, as in base 2, equals minus 128 coming from here. Add this unsigned value, which is minus 42. Is that okay, Matthew?
Yeah, steps are clear. I think I get how to do it.
Okay, and now let me take this opportunity to show another thing, another way. So this one, okay, how do I do it? Okay. Da, 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 da. Okay. So let's say we get a bit pattern 1, 1, 0, 1, 0, 1, 1, 0. We know this is a negative number from 2's complement perspective. This is a negative value. What we'll do, we basically invert this bit pattern. So make 1 to 0, and 0 to 1. Okay, and add 1 on top of this. These are all binary addition we are talking of. So right now we'll be talking about the binary addition process, etc., towards the second half of this semester. But I'm giving you a sneak peek of doing a shortcut, and I hope through some other courses you probably kind of familiar with the binary addition process. Maybe, may not be, doesn't matter, but we'll do it. But the process here is this: like we basically add this bit pattern. So we take the original bit pattern, invert it, add 1 top of this. So this becomes your 1 plus 1 is 1, 0. This 0 is this, and 0, 1, 0, 1, 0, 0, which is basically what? Like this is like 2, 4, 8, 16. This is 32. So that means we add them up. This is 42. So this bit pattern is value is 42, but we know that is a negative number, right? This is because this is a leading 1 there. So that means my original bit pattern, this guy, is minus 42. So that's an alternate way of handling it from logical handling of bit pattern perspective. And we'll be dealing with that more in towards the second half of this semester, when we start reviewing how the addition, integer addition happens, integer subtraction happens, and so forth. During that time, we'll deal with it. Question? Okay. Since we don't have a question, and let's go with the poll first. Launch poll. Let's take a minute. 44 participants, not bad. Class preparedness for today's topic. A few seconds left. 41 has been completed, voted. And you can do it anonymously. I have said that, so that's okay. Okay, let me close the poll. So, and share the result with the class. So basically about 48% said all of you actually watched the video lecture. That's good. Thank you very much. 5% none of them. Please make sure you watch it. Otherwise discussion may go, like you won't follow up the discussions that we made in the class. You are supposed to, this is kind of a flip style class. You need to study upfront before you come to the class. Some of them is 48%. So please make sure you got time to watch those videos. Same goes with the review, the lecture topics, etc. There are some questions noted, and most of you don't have a question. That means you're actually, I don't know what's going on there. I hope you will generate more questions to me. Anyway, so let's do this thing today in our class. is solve couple of problems. Maybe in a group, and I'll try the breakout rooms as well for this. So my first problem would be, okay, let me give two problems together. One is this. Oh, okay, and another would be okay. So the first problem, let me just make it a bigger font. I don't know. This fine. So first problem was like there is a 24-bit ALU, has two operands, OP1, OP2, and it has like supports 12 operations and encoded as in the input OPRN. You need to draw a schematic diagram of this ALU. You can use a piece of paper to draw the diagram and show it to me, and or share it to class. The other problem is that a processor executes instruction using 5-stage instruction execution cycle, the one we discussed last 2 days that we went through that process. Now this processor is running on the 1.6 gigahertz clock, and how long this processor will take in millisecond unit to execute 5 million instructions? That's the second problem. So what I'll do, I will create break rooms. So you have about 43, maybe about 4 person per room. Let me see if I can create. Okay, how do I create break room? Oh, breakout room. Okay. Maybe that means 44 for about 11 room, 3 to 4 create rooms randomly assigned. And we'll take, let's take 10 minutes to you discuss among yourself, come up with solution, and then we'll rejoin. Okay, so option breakout room close automatically after 10 minutes. Okay.
Professor?
Yes.
Can we find these problems anywhere so we can see them in the breakout rooms?
They're on the Jamboard.
Oh, okay.
Yeah, it's in the Jamboard.
Perfect, thank you.
The Jamboard? Or I can, is it like if I type it in the chat, will it accessible to you in the break room? Do you know?
Yeah.
Okay, let me also, why don't I just type in the chat as well. This is first problem. And this is next problem. Okay, so yeah, now I'm opening. This is 10 minutes. I have set that options to 10 minutes. And then we'll come back and discuss. Okay. So I hope you had a good discussion session with your peers on these problems. Anyone? Okay, let's wait for others. So did everyone come back? No. Okay. Let's wait a couple of seconds, about 20 seconds, to join others to join in. Okay. So who wants to go with the first problem? Anyone? No one has solved that problem? Schematic drawing?
We tried it.
Okay, so what's...
Do you want me to like draw it on the whiteboard or something?
No, you can draw in a piece of paper and just show it on the camera and see. Let's see.
Okay, I'll try to make a neater version real quick because the one I drew is kind of hard to read.
Oh, that's okay, I think. Okay, yeah, I'll give you a couple of seconds to do so.
So,
So what I'm planning, like later, like once the class list is settled down, then we'll assign Canvas groups and we'll assign breakout rooms for, you can like form a study group and stuff like that. And then establish a collaboration link to maybe through the Google Drive or Google Doc so that you can work on that document as a group on on this breakout session. Okay, let's look at Kevin's solution.
is that clear?
Yes. Okay, so what you did is basically operand 1 to 24-bit each. So why operation is 12-bit? Why do you need that?
We assume that when it said it also supports 12 operations, that it had something to do with that.
Okay, so basically, yeah, that's correct in the sense that, okay, you are assigning each bit to represent one operation. So what would be the minimum number of bits needed in that operation code?
4 bits.
4. Why?
Because the maximum value of a 4-bit number is 16, and that's just over 12. If you had 3 bits, it would be only 8.
I think
Right. So basically, Kevin, did you get it? Like, so 12 is okay from hardware perspective. I'm assuming that you are assigning each of the bit to represent one of the operations. So you are assigning 12 to it. But you can do it in a minimalistic way with a 4-bit. How do we come up with that? Like formally, if you take a log base 2 of 12 and take a ceiling, the log base 2 of 12 is a fraction number, 3 point something. And you take a ceiling value of that, that's 4. And that's what you need as a minimum number of bit on that LU operation port.
I see. All right.
So is that clear to everyone?
So just to be clear, you're gonna always write the minimum value? Like, is that the correct way to write it?
So basically, let's look at this question, right? This question does not say anything about the minimum value, right? So technically 12-bit is correct too. Now, if the question specifically asks that what is the minimum number of bits need to be used, then 12-bit would be wrong. It should be 4-bit in that answer, if it specifically says. However, it is always good to have a minimalistic approach. Like always think how you can do it with the minimum number of bits. Make sense?
Yes, thank you.
Okay, all right. All right. How about the next one? Number 2. Anyone wants to explain?
Sure, I'll explain.
Sure.
Can I get some clarification? Is each instruction one clock cycle? Is that what we're assuming here?
Each instruction. So is that your assumption?
Oh, well, yeah, I think we were assuming, oh, I guess it says instruction, not operation, right? So it's maybe a little more than one clock cycle.
Right, right. So basically, if you think like what we discussed previously, so let me share quickly with you. So this is Matthew, right?
Yeah.
So where is my share? So if you follow this discussion, right, on August 26, we did that. So one instruction actually need to go through the 5 cycles.
Yeah.
And cycle is takes one clock cycle. That should be your assumption.
Oh, okay. So it doesn't change much of the work that we did then.
Yeah.
Well, the first thing you would need to do is get the time period, which you can do since they gave you the speed of the clock. And the time period is 1 over the frequency, which is, I guess, the speed is also the frequency, right? So gigahertz is a frequency. So 1 over 1.6, and we would putting it in nanoseconds. So 1 over 1.6 is 0.625, and if you convert giga to nanoseconds, it just cancels out the 10 to the 9, so it's 0.625 nanoseconds. There's 5 million instructions, and each one takes 5 clock cycles, so you would do 0.625 nanoseconds times 5 clock cycles times 5 million times. So I'm not sure what the answer is, but I can get it for you.
So it would be around 15.625 milliseconds.
Yeah.
So yeah, right. So basically, let me re-explain a little bit on this one. Okay, let me share the Jamboard.
I have it written down as well if you want.
Okay, so can you share? Is it on your computer? You can share your screen, or
yeah, I have I can show I was writing on a tablet.
Okay.
So I don't know if you guys can see, but
yeah,
so,
sure.
It's kind of like hard to show, but there's the formula for time period. This is just the small, math to find the time period. There's our time period. And then below was what we thought was, we thought that you had to just times it by 5 million, but since it's instructions, not operations, so you have to times it by 5 clock cycles and then times it by 5 million. And then there's
Exactly.
Okay.
Thank you. Yeah. So basically the trick is that you need to make sure that it is not one clock cycle in one instruction, but each instruction is executed in a 5 cycle. The instruction fetch, instruction decode, register fetch, execute, memory, write back. So it always goes through this 5 cycle in this model. And the question also said this is the 5-stage instruction execution cycle. Each stage take 1 clock cycle. So 5 multiplied by 5 million instruction multiplied by clock period. That's what it give you the answer of total amount of time. And on top of that, you need to make sure you basically preserve the units. They are very important. Okay, so you will be converting between nanosecond, microsecond, millisecond. So you need to be very clear of this unit, what unit and how to convert from one each other. Okay, so please be mindful on that and practice a lot on that part. Okay, all right. Now, maybe we can take a 5-minute break at this point. We'll come back with maybe one more problem we'll do as a breakout smaller group, and we'll do that. Any question before we go into the break? Christopher has a question on the chat. Reason multiply by 5 is because the problems talk about 5-stage execution, 5 clock cycle per instruction. Yes, exactly, exactly. So you go back to our previous discussion, how one instruction get executed in the processor. So yes.
I have another
Let's
question.
take, yeah.
Do you think it'd be possible to write the answer down on the Jamboard later?
Yeah, sure. Answer, actually, this problem is your lecture problem set 1, 2,
Oh.
problem number 6.
Oh, I see. All right.
Yeah, you can look at the solution there. Okay, let's take 5-minute break. About 6:47-ish. We'll be back. Okay, so let's come back from the break. And I just copy paste the solution for number 2 onto the board. And for number 1 is easy. Like, why don't I do that on board? So basically what is need to be done. So this one for this, and for this problem, we have the ALU and since it is 24-bit, it has 2 input OP1 as description, OP2, each of them 24. And then it has 2 output V1, V2. Being 24-bit ALU, it will both be 24-bit. And on the operation side, if we want to go with the minimum number of bit, it is log base 2 of 12, which is coming from here, 12 operation. Take a ceiling of it, which is 4. So that becomes a 4. So this is the schematic or interface diagram for the ALU. You can also draw, if you don't want to draw this specific structure for the ALU, you can always draw a box like this. (24, 24, OP1, OP2, OPRN of 4, V1, V2, each of them 24-bit. But in this case, you need to make sure you put somewhere the name of this component. So that's the deal with the rectangular boxes. You need to specify what component you are talking of there versus the ALU, a very specific symbol, a schematic symbol for the ALU. So everyone knows what that component is. All right, saying that, let's take maybe another problem.
Could I see the thing again for 10 more seconds?
Yeah.
Got it. Thank you.
Okay.
Is there any difference between the two diagrams? Like, is there one that's like preferred, or?
Not really, not really. So it's up to your choice.
Okay. All right, thank you.
Okay. So let's do this problem. Oh. Normal. How do I change the font?
I have another.
No. Wait. Okay, let me clear the frame and let me try to.
If you paste with Control-Shift-C, it won't save the formatting.
Okay.
Control-Shift-V, I mean.
Control-Shift-V. Okay, let me try that. Control-C, Control-Shift-V.
Well, I guess it just auto shrinks it then.
Yeah. Oh, no. It is basically now I can at least, yeah. Now you all can see it, right? At least. So it has like a couple of sub problems there. Let me read it out to you, and then you can go to the breakout session to discuss among yourself. So we are talking about 32-bit, 1.6 gigahertz, just like the previous problem we did that processor with 1.6 gigahertz. So you have this clock period calculated already. Computing system has half-word addressable memory. So which means each address is half-word long, and or each address contains half-word amount of information, which is like 16-bit and 40-bit address bus. Now this memory takes 2 clock cycles to complete read or write operation, and processor takes 1 clock cycle to consume data from the memory. Like if it is a read operation, once the memory gives back the data, processor takes 1 more clock cycle to like register that data or consume that data in a general sense. During the operation with a single instruction, this processor generated a 2.5 million. This is actually 10 to the power 6, by the way. I don't know how to change it to, but this is the, 1 million is 10 to the power 6. Continuous read and write operation. Among these read-write operation, 40% is the read, and 20% of the write operation requests are successor of the read operation request. I mean, read operation immediately followed with the write operation in the next cycle. So that's the 20% of the write operation has such scenario. Side note, this type of memory access known as a DMA or direct memory access, not included in our study, but okay, doesn't matter. Doesn't matter in the problem. Clock period we already calculated in the previous, so it's the same clock period we're talking about here. Let's focus on this problem B and problem C. Calculate the memory size in gigabyte unit, make sure your units are right, and C is how long will it take to complete that 2.5 million memory access in a millisecond unit. Question on this problem. Okay, so let's take 10 minutes on these two problems. So no problem A, this doesn't matter. It is coming from the previous problem, same clock period, 1.6 gigahertz. And we have, let's take 10 minutes to ourselves. So let me open up the room.
Hello. I don't think I jumped into a breakout room.
Professor Patra?
Yes.
I have a question.
Yeah.
When it says processor takes 1 clock cycle, is that what we're using to multiply?
That's what you'll be using for the adding extra clock cycles. Those situations, like when a read request is completed and before processor can issue a write request immediately after that read request, it need to wait for a clock cycle to consume the read data. So that's where you will be needed to add extra clock cycles to the whole process. Is that your question?
Would you count the memory's clock cycle too?
We are assuming like they are operating on the same clock, so it doesn't really matter. Like which clock
Oh, so
cycle.
you would just use 1.
Yeah. Those type of problem, other complex problem where basically memories and the processor running on a different clock. But let's not complicate our life at this point.
And then for earlier, you know when we draw a diagram for a 24-bit ALU, why do you take the log of base 2?
Because that's how you determine the number of bits. Because
it's always log base 2?
Yeah.
Okay, so the default is log base 2. You keep mind of that?
Yeah, so basically it's a power of 2 operations in the binary world. So we always take like if we want to do the reverse calculation, we need to take log of into base 2, log base 2.
And I read somewhere where you to find your nanoseconds, you do 1 divided by your number times 10 to the 6th power.
So 1 nanosecond is basically 10 to the power minus 9 second.
9th second.
Yeah. 1 nanosecond unit is basically 10 to the power minus 9 second.
Oh. Okay. Thank you.
Okay, no problem. So you're not joining the breakout session? Aguirre? Okay, I think everybody, okay, close in 25 seconds. So let's wait for 25 seconds for everyone to come back. Did everybody come back? There are a couple. Okay. So who wants to give the answer for the first one, that calculate the memory size in gigabyte units?
I can do it.
Okay. What's your answer?
Hmm?
What's your answer? Final answer on that?
My final answer is 2048 gigabytes.
Okay, wonderful. So do you want to share your calculation?
Yeah, so we have an address buffer of address bus rather of size 40 bits. So the maximum address is 2 to the 40.
Okay.
And then since the memory is 2 bytes each, it's 16 bits, half word, then that means we multiply 2 to the 40 by 2 bytes, and that gets you 2048 gigabytes.
Okay, okay, that's good. So everyone get that, or do you have a question?
Wait,
So oh, never mind.
no, go ahead, sorry.
Like in a real memory, I guess, system, would it be typical for like every address to be used, or would it usually have like some blank addresses?
Yeah, there can be, okay, there can be blank address means, okay, what do you mean? Okay. Oh,
Like,
every address is actually pointing to a physical device, right?
yeah, like, is that the case, or would like some of the addresses just not be?
That can be a case. Yeah, that's a valid case, right? But without anything very specific in a problem or given situation, we always assume that every address is basically pointing to a physical storage device and location, and we can use that address to store data there. Yeah.
Okay.
Is that physical part of the memory, is that very complicated? Like how they store specific things at that specific location? Is that pretty complicated?
Yes, it's complicated to be its own industry. So memory industry is a completely separate sector than the processor industries. And they actually come up with the technological advancement come alternately. Like one cycle, memory advances with the more faster, bigger memories, and another cycle, processor industry goes forward with which needed much more power from the memory side. So yes, memories are complicated, and it calls for its own industry.
Professor, can you explain why there was that 2 to the power of 40 when I forgot who, but when the other student was explaining the problem?
Yeah, Jeffrey, you want to go for that? You are muted. Jeffrey, you are muted.
Oh, sorry. So the problem says that there is a 40-bit address bus, which means that the address is stored as a 40-bit number, and the maximum value of a 40-bit number is 2 to the 40.
That makes sense?
Yeah.
So that's the number of elements in the memory.
I see. Okay.
Okay, so it's all about this number of address bus bit there. So that's, if it is 40 bits, so we assume there are 2 to the power 40 storage or addressable space there in that memory. And each address space contains half word, which is like 2 bytes. So it is practically become 2 to the power 40 multiplied by 2 bytes. And then we split them up accordingly what unit we are targeting. We were targeting gigabyte unit. So we split them up, like 2 to the power 30 is 1 G. So 2 to the power 30 is one part, another part is this 2 to the power 11. So 2 to the power 11 is 2048. So it becomes 2048 gigabyte of storage.
So when we're talking about address buses, is that the physical connection from the memory to the processor?
Exactly, they are.
So you said that the address size is 2 bytes because it is like a half word address, right? So like if it didn't specify it was a half word address, how would the address size like vary, or how would that mess with the calculations?
So half word is basically signifies that each address space containing like 16 bit or 2 byte basically as a unit size. So let me try to explain that. We have 2 minutes. Let me try to do that. So basically we are looking for, so this is the memory. Okay. Let's say this is the memory, right? And let's say it contains these storage spaces. So it really depends on how many storage spaces are there in, and each storage space, how many bits are stored. How many bits are stored? Let's say it is B. So your size is really N multiplied by B. So in this problem, it says that, okay, I have 40 address space, address bit, address bus, right? So now N becomes 2 to the power 40 and B is 2 byte because of this half word. Okay, so that means it is 2 to the power 41 byte, which is 2 to the power 11 multiplied by 2 to the power 30 byte. This 2 to the power 30 is a gig unit, gigabit, and 2 to the power 11 is 2448 gigabyte. So that's your answer. So is that answer your question?
So it's the half word that makes the address 2 bytes, right?
Is the half word, it says that each address contains the 16 bits.
Okay. All right. Thank you.
That's the one. Okay, I think we just hit our time, class time. So maybe we'll continue with the problem C next day, Wednesday, and see you all then.
Okay, thank you.
Thank you.
Okay, thank you.
Bye.
Thank you, Professor.
Thank you.
Thank you.
Thank you.